Now here for steam power cycle, in this part here we are looking at the regenerative Rankine cycle. So this is your regenerative Rankine cycle. So basically here you have a boiler, a steam turbine. Now in this case we have no superheater. So you can add in superheater if you want superheating steam, okay, or superheated vapor as state point 1, and actually it depends on the questions whether they do consider pressure, a boiler pressure which is at higher temperature or else. If it is at higher temperature, that means greater than the saturation temperature or the boiler pressure of boiler temperature at that, boiling temperature at that particular pressure, boiler pressure, then the steam is superheated. Remember, if the temperature is compared to the saturation temperature with respect to the boiler pressure, if it is higher, it is always superheated. Okay, you can only get a temperature that is equal to the boiling temperature or the saturation temperature. You will never get anything that is below than that. That means, okay, it's still liquid. No. So what is at the outlet of the pressure must be at least at its saturation temperature. Either it's wet vapor, okay, it's a wet vapor or wet steam or mixture of liquid and vapor, or dry saturated vapor or superheated vapor at your point 1. So it goes into the steam turbine. It undergoes isentropic expansion as usual. So for regenerative, what happens is before the steam undergoes full expansion, somewhere in between point 1 and point 3 here, a certain amount of steam being extracted. The purpose is to heat up the saturated liquid that is leaving the feed pump from the condenser in order to raise up the pressure and the temperature slightly before it goes into the boiler. And then why regenerative? Because it will slightly improve the quality of the steam, okay, if it is with reheat, or it is to improve the main job or the main purpose here is to improve the thermal efficiency or the cycle efficiency of the power plant. Okay, so you have a turbine, and then in between 1 and 3, certain amount of steam is extracted, or we call this as black steam. Okay, so it will mix here in the mixing chamber here, and we call it as open feed water heater. Okay, so it mixes with the saturated liquid or the compressed liquid which is leaving the feed pump from the liquid which is from the condenser itself. So it's mixing. Why a mixing process here? Because in order to create, okay, the liquid of a slight higher pressure and slight higher temperature before it goes into the boiler, so that a certain amount of fuel can be saved up. Okay, so that you can save up a certain amount of fuel. So once fuel is saved, a certain amount of fuel is saved, then in other words, that means cycle efficiency is slightly improved, rather than, okay, there is no improvement here, as usual, running as usual, no open feed water heater, of course fuel consumption is slightly greater. Okay, so you have then up to point 3 where it undergoes full expansion, then it goes to condenser, constant pressure cooling, and then goes into the pump, isentropic compression to the feed water heater. Mixing process takes place here, produce liquid at 0.6 and then pumped to the boiler pressure and temperature, isentropic compression. So that means one open feed water heater, you have 2 feed pump. For reheating, every 1 reheater you add in, we have 2 turbines. Okay, every 1 reheating you add in, you need extra turbine. Here, each open feed water heater you add in, you need to add in 1 feed pump. Okay, so this is your dry saturated regenerative Rankine, where you can see your point 1 here is dry saturated, and then full isentropic expansion, even though a certain amount of steam is extracted from this point 2 here. So you have X amount of steam extracted or taken out from the turbine. So the remainder will be to 2 to 3 and 3 to 4, which you are having now 1.x kg only. So initially you can assume as 1 kg or any value up to you. Okay, 1 kg or 2 kg or A kg or B kg, up to you. Or x kg, how much you extract, how much of steam, how much of blade steam, or how much of hot dry steam you extract from the turbine. Okay, so you can put it as x kg, A kg, B kg, Y kg, up to you. Then the remainder should be 1 minus of that amount that you have extracted. So based on this diagram, now you can see here 1 to 2 is where you have your work output, and 2 to 3 also your work output. So your work output from 1 to 2 is still 1 kg, but 2 to 3 is no longer 1 kg. It is only 1 minus x kg. So that means your work output must have H1 minus H2 multiplied by 1 kg, and H2 minus H3 multiplied by 1 minus x kg. So point 1 here in this case is dry saturated, 2 wet, and 3 is wet. So how are we going to do this? H1, you can straight away take Hg, which is based on the boiler pressure, and then S1 also based on the boiler pressure, which is equals to Sg, which is also equals to S2, which is also equals to S3. Okay, so the working as later on, I'll show you the work later on in the later part. This is the theory part. Get the work examples later on. So this is your heat supply. Here you don't have reheater, don't have superheater, so straight away you take 1 minus 7 or 1 minus 6 if you were to neglect the feed pump. Okay, if you will neglect both feed pump, so straight away you can take H1 minus H4 or H1 minus H6. Okay, then work output, you should take H1 minus H2 times 1 kg, this case, then H2 minus H3 times 1 minus x kg. So that is your work out, work in, heat supply. Okay, so heat rejected is based on 3 to 4, that is your condenser, this is your condenser. Okay, so now, how much do we extract? How much of steam do we take out from the turbine? So assume as x kg. So from the compressed liquid, from the condenser and the feed pump, the first feed pump, you have 1 minus x kg remaining. This is how much you extract based on the diagram that we have just now, this part here. Okay, so this is one line going in, another line going into the mixing chamber, and this is a line where it is leaving the mixing chamber. So here you extract x kg in this line, and this line here which is going into the feed water heater remain only 1 minus x, and here you actually have 1 kg, back to 1 kg. So based on energy balance, this is in and this is in. So you must take xH2 plus 1 minus x times H5. Okay, actually. So this is what you have here. M2H2, the mass at this stream here, times the H2, plus the mass of steam that you have here, times the H5, equals to the mass in the stream 6 here, M6 times H6, the enthalpy at this line. So we know that our M2 is x kg. We know that our M5, that means here, is 1 minus x kg. And we know that our M6 here is 1 kg. So put it in. So manipulating the equation, So the X, put it at one side, those without X, put it on the other side. So from this equation, actually you can find out how much of steam you need to take out from the turbine, can take out from the turbine. So that means you must find out your enthalpy at every each state point before you can find out the X. This is the amount of steam that is taken out, not the dryness fraction. This is not referring to the dryness fraction. And then you can find out the cycle efficiency, work out, work in, okay, heat supply, heat rejected, everything, SSC, specific steam consumption, and so on. So the first thing is you must know how to find H1 to or the rest of the enthalpy at every each state point. Okay, so thank you.